Bauxite undergoes refining to extract alumina oxide, where impurities are dissolved, and filtration yields a purified white powder. This alumina oxide is smelted at high temperatures, around 700 degrees Celsius, in a process using electrolysis to extract aluminum, ensuring utmost purity with stringent quality control. The molten aluminum extracted via electrolysis is tapped into immense ingots, measuring around 9 meters long and weighing over 30 tons, forming the raw material for further shaping and processing. The large aluminum ingots are transported to undergo scalping and sawing processes. They are trimmed and cut into 10-ton blocks to facilitate their transformation into usable aluminum coils for printing plate production. The ingots are preheated to approximately 500 degrees Celsius to ensure uniform temperature distribution, vital for the subsequent hot rolling process to reduce their thickness effectively. During hot rolling, preheated ingots are rolled at temperatures around 500 degrees Celsius, reducing their thickness to about 4 millimeters and extending their length to around 2.4 kilometers. This process requires precision to ensure uniform thickness throughout the aluminum sheets. The resulting 4 millimeters thick sheets are rolled into coils, each assigned a unique code, and allowed to cool before progressing to the cold rolling section for further reduction and preparation for printing plate production. In the cold rolling phase, the aluminum coils from hot rolling are further reduced to the desired thickness, typically between 0.15 to 0.3 millimeters. This precision process readies the coils for the subsequent coating stages to transform them into printing plates. Shipping coils to coating plants. In the coating process, aluminum coils are unwound and subjected to surface cleaning, electrochemical treatment for roughening, and a computerized application of a light-sensitive coating. Quality checks, including CCD or laser inspections, ensure perfection. The coated aluminum is trimmed, cut, covered with protective sheets, and inspected before packaging as printing plates ready for shipment. During unwinding, aluminum coils are gradually released, beginning the coating process, essential for transforming them into printing plates. Aluminum undergoes an etching process to clean its surface thoroughly. Electrochemical graining roughens the aluminum surface for lithographic behavior. A light or thermal-sensitive coating is precisely applied to the aluminum surface, forming the medium for the eventual printed image or text, crucial for printing plate functionality and quality results. The coated aluminum undergoes meticulous quality checks using CCD or laser inspection systems, ensuring every square nanometer meets rigorous standards, with non-standard plates automatically identified and sorted out for perfection. Visual inspection involves a comprehensive examination of the coated aluminum plates, ensuring they meet exacting standards. Specialists scrutinize the plates for any imperfections, guaranteeing top-notch quality before the plates are trimmed, covered for protection, and readied for shipment to customers. After thorough inspections, the coated aluminum undergoes precision trimming and cutting to attain the required size for printing plates. Final inspections verify quality, after which the plates are covered for protection, boxed securely, and transported to customers, ensuring integrity throughout transit. The sand used is derived from a specific blend, gathered from termite mounds. This choice of sand isn't arbitrary. It's a deliberate selection owing to the composition found in termite mound sand. It contains a unique mixture of clay, soil, and other organic elements, contributing to its cohesiveness and malleability when mixed with sea sand. Artisans begin by carefully cutting a mound of sand in half, effectively creating two symmetrical parts. These halves are intricately tied together, creating a hollow space within. This hollow space is the canvas upon which the pots will take form. The termite mound sand, with its clay-rich composition, is then combined with sea sand, which complements it by offering a balanced texture and cohesiveness. This fusion of sands isn't just a random blend. It's a careful concoction that balances the properties of both types to achieve the ideal consistency for molding. The craftsmen pack this sand mixture around the cut sand halves. Every gesture, every compression of the sand mixture around the halves contributes to the eventual structure and shape of the mold. This process demands precision and a keen eye to ensure that the sand is uniformly packed, leaving no room for imperfections that could affect the final product. The resulting mold, formed by this delicate interplay of sands, exhibits the artisan's intimate understanding of materials and their potential. It's a testament to their resourcefulness, using locally sourced elements and traditional techniques to create a foundation for the subsequent stages of the pot-making process. To ensure the successful casting of the pots, the artisans begin by creating a bed, a foundational layer upon which the sand mold rests. This bed serves as a stable platform, essential for the subsequent steps in the casting process. Precision is key here, as any irregularities or unevenness in the bed could affect the mold's integrity. To prevent the sand mold from sticking and ensuring a smooth separation after casting, the craftsmen employ a clever technique. They line the mold with a protective layer, using a tent material and a small piece of tin. This lining acts as a barrier, preventing the molten aluminum from adhering to the mold, enabling an easier separation later in the process. Once the protective lining is in place, the craftsmen create a hole in the sand mold. This hole serves a crucial purpose. It acts as a channel or conduit through which the molten aluminum will flow into the mold. The size and placement of this channel are determined with precision, ensuring the even distribution of the aluminum within the mold, enabling it to take the shape of the pots accurately. These collected aluminum scraps undergo a transformative process where they are melted down. The artisans employ a methodical approach, utilizing furnaces or smelting techniques to subject the collected scraps to intense heat. Gradually, the aluminum reaches its melting point, transitioning from solid to liquid form. The craftsmen carefully monitor the temperature, ensuring the aluminum attains the ideal molten state for casting. Once the molten aluminum reaches the desired consistency, the craftsmen move swiftly to the casting phase. With the sand mold prepared and the channel set for pouring, the stage is set for the pivotal moment. The craftsman handles the crucible containing the liquid aluminum with utmost care, aware of its searing heat and the critical timing needed for casting. With precision and expertise, the craftsman pours the molten aluminum through the designated channel into the waiting mold. The liquid metal flows seamlessly through the channel, filling the mold's cavities and intricacies, taking on the shape and contours defined by the sand mold. This pouring process requires finesse to ensure that the aluminum spreads evenly throughout the mold, capturing every detail and intricacy of the pot's design. As the molten aluminum cools within the mold, it solidifies, capturing the essence of the craftsman's skill and the traditional techniques used in its creation. The successful pouring and subsequent cooling of the aluminum within the mold mark a significant stage in the transformation journey, as the raw material transitions into the recognizable form of handcrafted aluminum pots, embodying both functionality and cultural significance. The process begins with cutting the raw material into appropriate sizes and shapes, usually utilizing sheets or bars of high-quality steel or alloys. This stage aims to create the initial blanks that will eventually be shaped into knife blades. The next step involves forging the blanks into the rough shape of a knife. This is often done using a combination of heating and shaping techniques, either by hand or through machinery, to form the basic structure of the blade and handle. Following the forging process, the rough shape of the knife is refined by cutting out excess material and removing any burrs or imperfections. This stage involves creating perforations or holes in the blade, often for aesthetic purposes or to reduce the overall weight of the knife. The process may include drilling or punching holes in specific patterns. The hardening process is pivotal in fortifying the knife blanks. Controlled heating, often to precise temperatures, alters the steel's molecular structure, enhancing its hardness and durability. Rapid cooling or quenching solidifies these changes, locking in the desired properties. This transformation significantly elevates the blade's strength, enabling it to withstand rigorous use, while the enhanced hardness contributes to prolonged edge retention. The meticulous control of temperatures and cooling rates during this step shapes the very foundation of the blade's performance and resilience, ensuring a superior end product. After hardening, the blades might need straightening to ensure they maintain the correct shape and alignment. This step is essential for achieving uniformity and consistency in the final product. The blade grinding process involves shaping the edge of the knife to its desired sharpness and profile. Simultaneously, the back or spine of the blade undergoes grinding to smoothen and refine its surface. This step ensures that both sides of the blade achieve a uniform thickness and finish. The blades are carefully dried to remove any moisture that might have accumulated during the manufacturing process. This helps prevent corrosion and ensures the blades are ready for further refinement. For knives with a bolster, a preliminary grinding process is carried out to shape and refine this part of the knife, which adds strength and balance to the blade. This step involves further refining the blade's edge and ensuring it achieves the desired sharpness. Specialized tools and techniques are employed to create a precise and keen cutting edge. Leaning refers to the process of polishing or smoothing the blade's surface, removing any remaining imperfections and enhancing its appearance. Handles are assembled onto the blades. This might involve attaching scales made of various materials, like wood, plastic, or metal, to the tang of the blade, often using adhesives or fasteners. The final stage involves meticulous hand finishing of the handles. Craftsmen focus on shaping, sanding, polishing, and detailing the handles to achieve a comfortable grip and a visually appealing finish. The steel rolling process involves shaping heated ingots or billets through multiple stages of rolling mills, cutting, cooling, and straightening to achieve desired dimensions and qualities in the final product. The reversible duo mill in the roughing stage is a critical component in the steel rolling process, primarily responsible for the initial shaping of the ingot. It operates with immense power, often equipped with high-capacity motors, rollers, and precision controls. During roughing, the ingot, preheated to optimal temperatures, enters the reversible duo mill. This mill consists of multiple stands or sets of rolls that progressively reduce the ingot's size and shape. The rolls exert significant pressure on the ingot, gradually elongating and shaping it into a preliminary form known as a semi-finished product or a billet. The reversible aspect of the mill is crucial. It allows the rolls to rotate in both directions, enabling the ingot to pass back and forth through the mill. This bidirectional movement ensures a more uniform reduction in thickness and a consistent shape throughout the process. The roughing mill's rolls are often designed with specific profiles to achieve the desired dimensions and surface quality. The powerful motors driving the mill provide the necessary force to deform the steel, effectively compressing and elongating it. The cooling pit plays a crucial role in the steel rolling process by efficiently regulating the temperature of the rolled steel after it emerges from the furnace. As the heated steel leaves the furnace, it enters the cooling pit, a designated area where controlled cooling occurs. This pit utilizes various cooling mediums such as water, air, or a combination, allowing the steel to gradually decrease in temperature. Controlled cooling is vital as it helps to alleviate internal stresses within the steel, enhancing its strength and durability while preventing structural deformities during subsequent processing stages. The pusher furnace is a high-temperature chamber where steel ingots or billets are heated uniformly, using a pushing mechanism, ensuring consistent temperature for subsequent rolling processes. The finishing reversible duo mill is a pivotal stage in steel rolling, where the semi-finished product from earlier stages undergoes precision shaping. This mill operates similarly to the roughing mill but with finer adjustments and increased accuracy. Equipped with advanced rollers and controls, it refines the semi-finished product, achieving precise dimensions, surface quality, and final shape. This reversible mill also enables bidirectional movement, allowing the steel to pass back and forth, ensuring uniformity and a controlled reduction in thickness. The output from this stage forms the basis for the ultimate steel product's specifications and quality. The cutting saw is a pivotal tool in the steel rolling process, employed to precisely slice the rolled steel into specific lengths or shapes. Equipped with sharp blades and precise controls, the saw operates with accuracy and speed, ensuring clean and defined cuts. It accommodates various cutting methods such as abrasive, oxy-fuel, or high-speed blades, tailored to different steel types and thicknesses. Its versatility allows for the creation of diverse steel products from bars to customized lengths, meeting stringent dimensional requirements crucial for various industrial applications. The cutting saw significantly contributes to the final form and usability of the rolled steel. The bar straightening machine is a vital apparatus in the steel processing line, designed to refine the shape and alignment of steel bars. As the rolled bars emerge from previous stages, they might exhibit slight bends or deformities. The straightening machine employs rollers or presses that exert controlled force, effectively realigning the bars to meet precise straightness criteria. Equipped with sensors and precision controls, this machine detects deviations in bar alignment, applying corrective pressure to achieve optimal straightness. Ensuring uniformity and eliminating deformities, the bar straightening machine enhances the steel bar's structural integrity and usability across various industries, including construction and manufacturing. Raw material preparation at the outset, Alpina Group's advanced steel plants produce continuously cast round steel billets, each boasting a diameter of 230 millimeters. These billets serve as the foundational material for the production of high-tech seamless pipes. Most billets undergo precise cutting using carbide-tipped saws to meet required lengths. However, a select portion of billets undergoes a preheating process before being precisely cut to length. This preheating step prepares the billets for subsequent transformations in the manufacturing process. Forming steps. Piercing to rolling. The transformation of these solid round billets into seamless tubes involves a series of critical forming steps. 3 primary processes: crossroad piercer, push bench, and stretch reducing mill progressively shape the billets closer to their final seamless tubular state. Crossroad piercer. This initial step begins the transformation. The solid round billets enter the piercing mill, where the magic unfolds. Through the strategic use of mandrel bars and forming rolls, the billets are transformed into tube shells. These internal components, along with precise forming rolls, elongate the pierced shell, initiating the journey towards becoming a seamless tube. Tube elongation. This elongation process is impressive, stretching the pierced shell up to 17 times its original length. The result is now termed hollows, exhibiting varying dimensions, with wall thicknesses ranging from a minimum of 3 millimeters to a maximum length of 22 meters. Precision becomes an inherent aspect of this stage, with continuous monitoring of the wall thickness using radiometric gauges. This meticulous oversight ensures uniformity and adherence to specified tolerances, a crucial aspect of achieving high-quality seamless tubes. The hollows proceed through a computer-controlled walking beam furnace to attain the required rolling temperature for the subsequent stretch-reducing process. The 28-stand stretch-reducing mill imparts final geometrical specifications, defined diameters and wall thicknesses, to the tubes. The integrity of the rolling process is assured by verifying wall thicknesses across the entire length via radiometric gauges, ensuring adherence to specifications. Once the tubes are up to 150 meters long, they undergo rapid cooling, enabling specific mechanical properties. Carbide-tipped saws then cut these tubes to their final lengths, branching off for diverse applications in various industries. Raw material preparation. The process begins with the collection of raw materials, primarily iron ore, coal, and limestone. Iron ore is mined from the earth and refined into iron in blast furnaces, while coal is converted into coke. In the iron-making stage, iron ore is processed in blast furnaces along with coke and limestone. The furnace operates at high temperatures, around 2,700 degrees Fahrenheit, 1,500 degrees Celsius, causing chemical reactions that result in the reduction of iron ore to molten iron, also known as pig iron. The limestone aids in separating impurities from the molten iron, forming slag that floats on top and can be removed. In the BOF method, the molten pig iron from the blast furnace is poured into the basic oxygen furnace. High-purity oxygen is blown into the furnace, oxidizing impurities such as carbon, silicon, and manganese. This process removes excess carbon and other impurities, resulting in the production of steel. The process begins once the steel is refined to the desired chemical composition and quality in the steel-making furnace, whether it's a basic oxygen furnace, BOF, electric arc furnace, EAF, or another refining method. The molten steel at temperatures exceeding 2,600 degrees Fahrenheit, 1,427 degrees Celsius, is then directed to a continuous casting machine. Within the continuous casting machine, the molten steel is poured into a tundish, a reservoir that regulates and controls the flow of steel into a water-cooled copper mold. This mold is typically shaped according to the desired semi-finished product, whether it's a slab, bloom, or billet. As the steel flows into the mold, it starts to solidify against the cooled walls, forming a thin shell. Simultaneously, water circulates within the copper mold, rapidly cooling the steel to facilitate solidification. The continuous movement of the mold allows for a continuous extrusion of the solidifying steel. The semi-finished steel products are then processed further through rolling, forging, or shaping to produce final products like bars, sheets, rods, or structural sections. These finishing processes impart specific shapes, sizes, and surface finishes to the steel. Throughout the steel-making process, stringent quality control measures are implemented to ensure the final steel meets the required standards for strength, durability, and other properties demanded by different industries. Advancements in technology and increasing focus on sustainability have led to innovations in steelmaking, such as the development of more energy-efficient processes and the utilization of recycled materials, reducing the environmental impact of steel production. The hot strip mill at Essar Steel employs advanced rolling technologies to produce various steel grades, catering to customer specifications with precise sizing and enhanced mechanical properties. Essar Steel's state-of-the-art plate mill yields specialized, high-quality plates globally. The digital reheating furnace at Essar Steel ensures precise slab temperature control for superior plate properties. The 4HO reversing rolling mill at Essar Steel refines steel blocks, passing them through multiple stages to achieve precise plate sizing and fine-grained properties for customer requirements. Thermomechanically controlled processing involves accelerated cooling, refining steel properties for enhanced strength, toughness, and wear resistance in plates. Accelerated direct cooling and direct quenching at Essar Steel's facilities rapidly cool steel plates, enhancing abrasion resistance, mobility, wear performance, and tensile strength, ensuring exceptional toughness and durability. Shearing at Essar Steel customizes plate sizes to meet customer needs. Austenitizing at Essar Steel involves heating steel for optimal transformation properties. Normalizing, quenching, and tempering at Essar Steel refine plate properties, enhancing strength, toughness, and overall performance for specific applications. Ultrasonic testing verifies plate quality through sound waves. The transformation towards utilizing blooms predominantly sourced from the caster marked a significant shift in the mill's operations. Blooms, which originated from the caster, were transported on flats to the designated soak bay, a specific area predetermined by the soak controller for the soaking process. Upon placement in the pits, the blooms underwent a meticulous heating and soaking phase. The temperature and duration of soaking were crucial and varied based on the quality of the steel being processed. For instance, steel intended for leaded free cutting required a soaking temperature of 1,305 degrees, while those designated for tire cords were soaked at 1,275 degrees. Once the steel attained the ideal readiness for rolling, the vertical ingot crane, VIC, initiated the process by drawing the blooms from the pit. These blooms were then delicately set onto the ingot buggy, ensuring a well-presented front end to facilitate seamless milling operations. The primary mill, the initial stage of the process, meticulously reduced the stock's size through a series of passes and tilts. This mill directly fed the bloom into the secondary mill, employing precision passes and tilts to craft either finished sizes for sale or larger blooms for the continuous mill. Line scarfing was a critical process ensuring high-grade steel quality. Utilizing high-pressure oxygas, it adeptly eliminated surface defects from the steel, presenting a pristine front end for the continuous mill. This meticulous method played a pivotal role in enhancing surface quality, essential for the higher-grade material. By systematically removing defects from both the front and back ends of each bloom, line scarfing upheld stringent quality standards crucial for downstream processes and customer satisfaction. The roughing mill prepared blooms for subsequent stages through shaping passes. The intermediate mill played a pivotal role in refining the blooms from the roughing mill. Before entering, an inline tilter positioned the bloom on its diamond, crucial for the subsequent passes. Within this mill, a series of precision passes and tilts further shaped and reduced the bloom size, ensuring it met precise dimensional requirements. The assistant roller at the exit meticulously calibrated the product size, guaranteeing it aligned perfectly with customer specifications. This stage readied the bloom up to 90 meters long for the final stages of production in the continuous mill. Once the blooms, thanks to the unique V-rolls, progressed towards the finishing mill, attention was paid to ensure the product aligned with customer requirements. Rollers played a crucial role in monitoring the steel's quality, ensuring precision and compliance throughout the final stages. Exiting the finishing mill, the steel encountered the billet flying shear, a pivotal component cutting nose and tail crops, shaping the steel into user-defined lengths based on customer specifications. The steel then underwent stamping, where an inline machine imprinted cast numbers on each billet, aiding identification and traceability. Slabs and billets exceeding specific dimensions, an alternate route was taken to bypass the finishing mill. This route involved dropping the V-rolls and moving through the bloom flying shears, P9, towards a different transfer point known as T3. Once the steel reached this stage, it entered cooling banks, where it was hydraulically pushed onto racks and left to cool for a predetermined period. The bank's team leader marked the steel with special chalk, ensuring proper identification and enabling further cold processing. Subsequently, the steel moved to water-filled quench tanks for temperature reduction, preparing it for further inspection processes. From here, the steel had multiple routes available. Slabs primarily went to T18 for visual inspection, while higher-grade material underwent automatic inspection, distinguishing between various qualities like tire cords and forging grades. At T6 transfer, the steel entered the automatic inspection line, beginning with a roll straightening machine, employing pairs of rolls and hydraulic pressure to ensure bars met specific straightness criteria. Certain billet qualities, or those demanding superior straightness, underwent further straightening by an offline gag press before proceeding. Following straightening, bars went through an automatic shot blasting process before entering the thermo-montage house, equipped with state-of-the-art technology to detect defects outside customer specifications. Detected defects were sprayed with paint for offline rectification, maintaining product integrity. Each bar underwent color coding according to its chemical composition, aiding in maintaining cast integrity. Bars marked with defects required grinding for rectification. The grinders, installed in response to increasing customer demands, utilized high-speed rotating stones to remove defects. Additionally, stringent internal cleanliness checks and ultrasonic testing ensured compliance with high-quality standards, particularly for specialized applications like hydraulic systems. Slabs processed at T18 underwent rectification through de-seaming to remove surface defects before dispatch. The mill handled substantial quantities of billet cast product, necessitating processes like defauching, burning, and painting before dispatch. Upon achieving prime status, steel could be immediately loaded for transport or stored in stocking pens with substantial capacity. The 778 square kilometers catchment area encompasses the Spey Dam, Loch Lagan Dam, and Loch Traig Dam, integral components of the hydroelectric system supporting the Lochaber smelter. These dams collect hillside runoff through various intake points. The main tunnel, spanning 24 kilometers, facilitates water flow from these reservoirs to the smelter. This network sustains an impressive overall flow rate of 45 cubic meters per second, ensuring consistent and substantial hydroelectric power supply to the facility. The facility employs multiple 20 megawatts Francis turbines, contributing to a collective generating capacity of 100 megawatts. These turbines harness the kinetic energy from the water flow within the hydroelectric system. Operating efficiently, the Francis turbines convert this energy into mechanical power, which, through generators, produces electricity. Their combined output of 100 megawatts signifies a substantial and reliable power source for the operations at the Lochaber smelter. Aluminium oxide, is transported to the site through a gravity-fed system, relying on natural downward movement for delivery. The alumina cryolite solution serves as an electrolyte within the smelting cells. Carbon anodes, plus, facilitate the electrolytic process by releasing electrons upon contact with the molten solution. At around 800 degrees Celsius, the electrolysis breaks down the alumina, allowing oxygen ions to combine with the anodes, while the aluminum ions accumulate at the cathode, forming molten aluminum. This process separates and collects the pure aluminum, crucial for subsequent casting and manufacturing. Casting pans facilitate the creation of high-purity aluminum, typically reaching 99.9%. Each pan yields ingots weighing around 1,800 kilograms, ensuring consistent and quality-controlled output for manufacturing purposes. The hot rolling process encompasses several crucial stages, each contributing significantly to the quality and characteristics of the final steel product. Heating and reheating furnace. The process begins by heating the material, often a slab, in reheating furnaces to temperatures as high as 1,200 degrees Celsius. This critical step ensures the material reaches the necessary malleability for rolling. Roughing mill. The heated material is then rolled in the roughing mill, where it undergoes substantial reduction in thickness, typically from 22 centimeters down to about 3 centimeters. This reduction involves several passes through high-power rolling mills with backup and working rolls. Surface cleansing. Prior to further rolling, the material undergoes surface cleansing to remove any mill scale or impurities. High-pressure water spraying at around 160 bars effectively cleanses the surface. Finishing mill. The material, now known as transfer bars, proceeds to the finishing mill. Here, in a series of stands resembling 4 high-rolling mills, the bars are further rolled to achieve a final thickness between 16 and 1.8 millimeters. Vertical rolls and adjustable working rolls ensure precise control over width and thickness. Cooling and coiling. Upon passing through the cooling section, the strips are coiled at temperatures ranging from 150 to 750 degrees Celsius, crucial for determining the final material properties and microstructure. High-pressure water spraying. High-pressure water jets, typically operating at around 160 bars, are directed onto the material's surface. These jets effectively dislodge and remove the mill scale and any adhering impurities. The force of the water breaks down the oxide layer and other contaminants, preparing the surface for subsequent rolling processes. Purpose of cleansing. The cleansing process serves multiple purposes. Firstly, it ensures the removal of any residue from the previous stages that could negatively impact the surface quality. Secondly, it prevents the mill scale from being rolled into the material during subsequent passes, which could compromise the final product's surface finish and integrity. Quality control. Stringent quality control measures are in place to monitor and verify the effectiveness of the cleansing process. Transfer bars are a crucial intermediate product in the hot rolling process, serving as an essential stage between the roughing mill and the finishing mill. Dimensional adjustments. Transfer bars are often subjected to dimensional modifications to meet the precise width, thickness, and weight requirements for subsequent processing stages and the final product. Temperature control. Temperature is a critical factor. As the transfer bars are coiled in a coil box, the primary aim is not only to conserve space, but also to allow for temperature equalization. This process minimizes temperature differences across the material's length, ensuring uniformity. Trimming and surface refinement. The ends of the transfer bars are often trimmed to remove any uneven or unwanted sections. Further surface refinement might occur at this stage to ensure the removal of any residual mill scale or impurities before entering the finishing mill. Rolling and thickness reduction. The strips, having undergone significant reduction in thickness in the roughing mill, are further rolled in the finishing mill. This stage typically consists of multiple stands, often 6 stands arranged in the configuration of 4 high rolling mills. The rolls in these stands exert controlled pressure to reduce the strip thickness to the final desired range, typically between 16 and 1.8 millimeters. Profile and flatness control. To ensure precision in the final product, specialized equipment such as up loopers and horizontally adjustable working rolls are employed. Up loopers measure and control line speed and strip tension, while the adjustable rolls regulate the strip's profile and flatness. These adjustments are vital for maintaining consistent product specifications. Cooling and coiling. Following the final rolling passes, the strips pass through a cooling section. Here, the cooling rate is tailored to create the appropriate microstructure and material properties. The strips are then coiled at temperatures ranging from 150 to 750 degrees Celsius. This coiling process, conducted in a controlled environment, further refines the material's properties and prepares it for subsequent processing or direct sale to customers. The process begins with the melting of high-purity aluminum ingots in a furnace. Once molten, the aluminum is cast into rectangular molds to form large slabs called billets. These billets undergo a homogenization process in which they are heated to a specific temperature to ensure uniformity in the material's structure and composition, minimizing any inconsistencies. The billets are preheated in a furnace and then fed into a hot rolling mill. In the hot rolling process, the aluminum is gradually reduced in thickness and lengthened by passing it through a series of rolling stands at high temperatures, typically above 400 degrees Celsius. This process elongates and thins the aluminum, forming a continuous sheet or coil. To relieve stress and enhance the material's properties, the aluminum coil may undergo intermediate annealing, a controlled heating and cooling process. This step helps in achieving the desired mechanical properties and improves the formability of the material. The coil is then subjected to final annealing, where it's heated and allowed to cool slowly to further refine its microstructure and mechanical properties. Post-rolling, the aluminum coil undergoes surface treatment processes such as cleaning, trimming, and sometimes coating to meet specific customer requirements or industry standards. These treat Throughout the entire production process, rigorous quality checks and inspections are conducted. This ensures that the aluminum sheet meets the required thickness, mechanical properties, surface finish, and dimensional tolerances. Once the aluminum coil sheets pass quality control, they are packed according to customer specifications, safeguarding them against any potential damage during transportation.
The journey of a high-speed rail begins with the billets, which are cylindrical pieces of steel being discharged from the furnace. These billets are subjected to extreme temperatures, reaching up to 1250 degrees Celsius, to make them malleable for the subsequent rolling process. However, before they can be further processed, they must undergo meticulous descaling to eliminate impurities and oxide layers. This is achieved through the use of high-pressure water jets operating at a remarkable water pressure of 250 bars. This thorough descaling process is crucial for ensuring the purity of the steel and the quality of the final rail product. Once the billets are thoroughly descaled and cleaned, they are ready to enter the roughing train breakdown mill, commonly referred to as BDM1. Here, the first breakdown mill stand plays a pivotal role in reducing the billet size through multiple passes. This reduction process is carefully controlled and monitored to ensure safe and efficient rolling. Additionally, the billets are turned using a hook-type tilter to facilitate uniform rolling and maintain consistent quality throughout the billets. After the roughing stage, the billets move on to BDM2, where they undergo further reduction to meet close tolerance requirements. Grip-type tilters are used to turn the rolled stock, which is now significantly longer. The leading pass for the finishing train is ruled, and the drop saw may be employed to crop the rolled stock if necessary. Lateral transportation in the horizontal direction ensures precise threading into the roll pass. The heart of the rail manufacturing process lies in the CCS, continuous casting system, finishing stand. This stand group consists of two CCS Universal 2 high stands and a CCS edging stand, enabling the production of universal rails and beams using the X-age method. The universal rolling process ensures close tolerances, high surface quality, and minimal roll wear, all of which contribute to increased output. Hydraulic adjustment systems and automatic gauge control systems enable ruling speeds of up to 8 meters per second. The rails undergo 4 universal and 2 edging passes to achieve the desired shape and dimensions. Quality assurance is a top priority throughout the manufacturing process. Each individual rail is stamped with a unique number for traceability purposes. This traceability allows for the tracking of each rail's production history and materials used, ensuring that any potential issues can be quickly addressed. Additionally, rigorous quality control measures are in place to verify that the rails meet the specified dimensions and metallurgical properties. After finishing rolling, the rails are conveyed to the cooling bed, where they are cooled to a straightening temperature of 60 degrees Celsius. This controlled cooling process is essential to prevent thermal stresses and ensure uniform material properties. To improve straightness and minimize internal stresses, the rails are precisely cambered before entering the straightening plant. The straightening process is crucial in achieving the desired straightness of the rail. It plays a vital role in minimizing internal stresses within the rail, ensuring uniform alignment and structural integrity. The straightening process consists of 2 stages. Horizontal straightening. In the first stage, the rail passes through a horizontal straightening machine equipped with cantilever-type straightening rollers that are individually driven. As the rail moves through this machine, the straightening rollers exert pressure and carefully adjust the rail's position to achieve horizontal straightness. This precise control over the straightening process is essential to meet the required specifications. Vertical straightening. The rail then proceeds to the second stage, which involves the vertical straightening machine. Similar to the horizontal straightening machine, this machine is also equipped with individually driven straightening rollers. These rollers exert pressure and adjust the rail's position vertically, ensuring that it achieves the desired straightness. High-speed track rails in China are primarily supplied by 7 specialized works, but one company, SMS Group China, stands out as the leader in universal rail technology engineering and manufacturing. The SMS Group's plant in Inner Mongolia has been operating tirelessly for 12 years, producing over 8 million tons of rails for more than 50,000 kilometers of track. The core components of the manufacturing plant include a walking beam reheating furnace, a high-pressure descaling unit, and 2 breakdown mill stands. The first breakdown mill stand has a nominal roll diameter of 1,100 millimeters, a barrel length of 2,600 millimeters, and a roll force of 8 meganewtons. The second breakdown mill stand has an 850 millimeter nominal roll diameter, a 2,300 millimeter barrel length, and a 4.5 meganewtons roll force.
One, fully automatic billet loading. The process begins with the automatic loading of metal billets. These billets have a diameter of 240 millimeters and serve as the raw material for the pipe production. The automated loading system ensures a smooth and continuous supply of billets into the extrusion machine. 2. Precise billet positioning for front loader operation. To ensure the extrusion process's accuracy, precise billet positioning is crucial. The system aligns the billets for front loader operation, guaranteeing that they enter the extrusion process in the correct orientation. 3. Direct extrusion. Direct extrusion is the core of this manufacturing process. It involves forcing the metal billets through a specially designed die to create pipes with the desired shape and dimensions. This method ensures a consistent and high-quality output. 4. Multi-axis manipulator handling of dummy and scavenger blocks. During the extrusion process, the machine employs a multi-axis manipulator to handle loose dummy and scavenger blocks. These blocks help maintain uniformity and consistency in the extruded pipe's dimensions and quality. 5. Control panel with Pico's visual display system. The entire extrusion process is monitored and controlled through a sophisticated control panel equipped with a Pico's visual display system. This system provides real-time data and allows operators to make precise adjustments to maintain product quality and process efficiency. 6. Cooling table with walking beam cross conveyor. After extrusion, the freshly formed pipes move onto a cooling table equipped with a walking beam cross conveyor. This cooling phase is essential to stabilize the pipe's structure and prevent deformation. The walking beam system ensures an even cooling process. 7. High-performance finishing saw with extraction system and cutting gap adjustment. The extruded pipes then go through a high-performance finishing saw. This saw is equipped with an extraction system to remove any debris and maintain a clean working environment. The cutting gap is adjustable, allowing for precise cutting of pipes to meet specified lengths and dimensions. 8. Cross-transfer to moving deposit tables. Once cut, the pipes are transferred to moving deposit tables. This step ensures efficient handling and storage of the finished pipes, preparing them for further processing or packaging. 9. Optimum reproducible product quality. Throughout the manufacturing process, the primary goal is to achieve optimum reproducible product quality. Strict quality control measures are implemented to meet industry standards and customer specifications. This includes monitoring dimensions, surface finish, and structural integrity. 10. Hollows diameter, max, 150 ohm, and section width, max, 180 millimeters. The extrusion machine line is capable of producing pipes with specific parameters, including a maximum hollows diameter of 150 millimeters and a maximum section width of 180 millimeters. These specifications ensure that the produced pipes meet the desired industry standards and applications.
The journey of steel production begins with the mining of iron and coal from ANZ's own mines. These raw materials serve as the foundation for the entire process. Iron ore undergoes a pelletization process, transforming it into small balls known as pellets. Meanwhile, coal is processed into coke, a crucial fuel for blast furnaces that produce pig iron. The blast furnace is a towering structure standing over 160 feet high, internally lined with refractory bricks. It plays a pivotal role in the transformation of raw materials into pig iron. Iron oxides, along with limestone, dolomite, and coke, are deposited in layers within the blast furnace. Hot air is introduced under pressure, creating an environment of up to 1650 degrees Celsius. This process reduces and converts the raw materials into pig iron, which is collected and further processed. To eliminate sulfur content in pig iron, a desulfurization plant is employed. The slag generated during smelting is deposited in a slag pit, cooled with water, and can be sold as a byproduct. The conversion of pig iron to steel utilizes the oxygen-based basic oxygen furnace (BOF) technique and an electric arc furnace (EAF). BOF steelmaking involves loading scrap metal into pear-shaped refractory-lined converters, where molten pig iron is added and refined with oxygen, argon, and nitrogen. The EAF process begins with a mixture of scrap metal, iron briquettes, and liquid pig iron. This mixture is melted by applying 140 megavolts of electric energy through 3 graphite electrodes. The resulting liquid steel is poured into ladles, and alloying elements are added to meet specific customer requirements. Both BOF and EAF-produced liquid steel go through secondary treatment stations for further refinement, including reducing hydrogen and carbon content when necessary. After these treatments, the liquid steel is transformed into slabs through a continuous casting machine. This process involves passing the liquid steel through rollers with a cooling system until it solidifies into slabs. These slabs are then cut to the required dimensions. ENZA offers a variety of steel products, including steel plates, steel strip coils, and structural shapes. The hot strip line, which produces steel strip coils, involves reheating slabs and rolling them into the desired thickness and width. The cold rolling department further modifies the physical properties of the steel through processes like pickling, tempering, and tension leveling. ANZA also manufactures tinplate and chem-free steel, catering to the metal container industry. In both cases, cold-rolled coils undergo specific treatments to meet the unique requirements of these applications.
Once the area is identified, the initial step involves the removal of surface topsoil utilizing specialized devices like chambers or conventional machinery. This topsoil is later reused in the reclamation process to restore the mining site to its natural state. Crucially, stringent safety measures aligned with global standards are implemented to ensure the well-being of both the land and the workers involved in the extraction process. Following this, experts meticulously pinpoint specific locations for controlled blasting through passageways, setting up the necessary equipment and foundations for the detonation phase. This controlled explosion removes the surface soil, allowing access to the underlying phosphate layers. The extracted phosphate ore is then gathered using advanced mining machinery. It is transported directly to processing plants for further refinement. During the operational phase, an impressive 40,000 tons of phosphate ore are transported daily from the mining site through an extensive 14-kilometer conveyor belt to the processing facility. At the processing plant, the concentration of the phosphate ore is increased through sorting and beneficiation processes. This enhancement is crucial for the production of phosphate fertilizers, which cater to the global demand for agricultural needs. The company's expertise and efficiency in this process have positioned it as a formidable force in the global market for phosphate fertilizers. Their ability to meet these demands underscores their significance in the industry. Elwood Aluminium's integration of the holding furnace with the Wagstaff casting system represents a pinnacle in aluminum casting technology, catering to the demands of precision, efficiency, and quality control. The seamless fusion of these two components empowers the operation to achieve unparalleled control and flexibility, transforming the casting process into an orchestrated symphony of precision. At the heart of this innovation lies the Elwood Aluminum Holding Furnace, a meticulously designed crucible for molten aluminum. It serves as the core reservoir, maintaining the metal at the optimal temperature for casting. What distinguishes this furnace is its integrated functionality with the Wagstaff casting system. This synergy enables the control room operators to dynamically adjust the tilt of the furnace, a pivotal aspect in regulating the flow and distribution of molten aluminum during casting. The Wagstaff casting system, renowned for its cutting-edge vertical direct chill casting technology, stands as a testament to precision engineering. It operates in harmony with the holding furnace, ensuring the aluminum is cast with the utmost precision, resulting in superior quality products. The vertical direct chill casting technology facilitates controlled solidification from the bottom to the top of the mold, minimizing defects and ensuring a uniform microstructure, critical for high-quality aluminum products. The collaboration between Elwood Aluminum's holding furnace and Wagstaff's casting system epitomizes innovation in the aluminum casting industry. The ability to control the tilt of the furnace from the control room not only streamlines the casting process, but also enhances safety measures by reducing manual intervention, thus minimizing potential hazards. Moreover, the integration of these technologies allows for meticulous monitoring and adjustment of casting parameters. This level of control enables operators to fine-tune the casting process in real time, optimizing production efficiency and minimizing wastage. Elwood Aluminum's commitment to excellence extends beyond technological innovation. The utilization of state-of-the-art technology signifies a dedication to producing aluminum products of the highest quality. This amalgamation of precision engineering and cutting-edge technology results in aluminum casts that meet the most stringent industry standards. Homemade and affordable aluminum casting. Crafting possibilities from scrap metal. The allure of turning discarded pieces of aluminum into usable components has fueled the curiosity of many DIY enthusiasts. In the realm of home-based craftsmanship, the process of melting aluminum emerges as a cost-effective method, transforming overlooked scraps into versatile resources for various applications. This journey through the art of aluminum casting not only unveils the technique, but also illuminates the ingenious ways to harness its potential. The foundation lies in the remarkable ability to recycle aluminum fragments, transforming them into functional parts. This sustainable approach not only lessens waste but also offers a frugal means of acquiring material for diverse projects. While cast aluminum may not match the hardness of its extruded counterpart, its versatility makes it a valuable resource for specific needs. From motor supports to radiators, its utility spans various domains, rendering it indispensable for ingenious creators seeking practical solutions. Central to this endeavor is the creation of a melting furnace, an apparatus serving as the gateway to transforming solid metal into a malleable state. The video showcases an ingenious use of insulating fiber, sourced from a pottery kiln, to construct this essential furnace. However, an alternative method utilizing refractory cement, at a mere €12 for a 25-kilogram bag, presents an economically accessible pathway to achieving the same results. This innovation highlights the adaptability and resourcefulness inherent in the art of aluminum casting. The process unfolds as a fusion of creativity and craftsmanship. The video demonstrates the yet straightforward steps involved in preparing the furnace, creating an accessible entry point for aspiring artisans. The amalgamation of affordability and functionality becomes apparent as the furnace takes shape, embodying the spirit of repurposing materials into tools of productivity. The melting process itself holds a mesmerizing allure, as the aluminum pieces yield to the heat, transitioning from solid to molten. They embody the transformative power of ingenuity. This molten state becomes the raw material for the artist's canvas, awaiting its mold to give form to innovative designs. The fluidity of aluminum opens doors to customization, enabling the creation of unique shapes and structures according to individual specifications. Beyond the practical implications, this venture encapsulates the essence of DIY culture, a fusion of innovation and sustainability. It exemplifies the power of self-sufficiency, inviting individuals to explore uncharted territories within their own workshops. Through this process, the creator becomes both artist and engineer, sculpting functionality out of discarded remnants. Moreover, the underlying message of environmental consciousness resonates deeply. By repurposing aluminum, a material notorious for its environmental impact when discarded, the endeavor echoes a commitment to responsible practices. It transforms what might have been waste into a valuable resource, contributing to a more sustainable cycle of production and consumption. The manual process of crafting a non-permanent green sand mold for aluminum casting is an intricate procedure that demands precision and a keen eye for detail. This traditional method, although labor-intensive, remains a cornerstone in the production of precise aluminum castings. The process commences with the placement of the molding box, positioned with the ears facing downward, aligning it according to the specific model requirements. This initial step sets the foundation for the subsequent stages of mold creation. Attention to detail is paramount as the craftsmen manage the right-hand side of the molding box, ensuring precise measurements and alignments. Any deviations or errors at this stage can significantly impact the final product's quality. One notable aspect is the inclusion of separate powders or materials, indicated by a note behind, which subtly suggests adjustments or unique requirements specific to the company's standards. This signifies the adaptability and fine-tuning required in this craft, where even subtle variations can yield different outcomes. The process continues with the creation of holes in the mold, strategically placed to serve specific purposes in the casting process. The addition of fine powder in designated areas further refines the mold's characteristics, enhancing its ability to produce the desired aluminum castings. As the mold takes shape, attention is given to the compacting of the green sand around the model. This is a critical step, demanding precision and care to ensure that the sand encapsulates the model entirely, leaving no room for error. Any imperfection or inconsistency in this phase could compromise the final product's integrity. An interesting facet of this process is the incorporation of instruments like micrometers to measure the mold's hardness accurately. This measurement serves as a quality control step, ensuring that the mold meets the required standards for successful aluminum casting. Furthermore, the craftsman's skill is showcased in their ability to create walls within the mold using precise measurements and specific sand deposition techniques. This step requires a delicate balance between adding sand for structural integrity and avoiding excessive amounts that could complicate the casting process. Turning the mold is a delicate maneuver that demands coordination and finesse. The craftsmen carefully rotate the mold, taking precautionary measures to avoid any damage or misalignment that could affect the casting's outcome. This step emphasizes the importance of teamwork and synchronized actions in achieving a flawless mold. Another crucial aspect is the securing of the mold using bolts, ensuring its stability and structural integrity. Attention to detail during this phase prevents any mishaps or deformities during the subsequent stages of the casting process. Throughout the process, the craftsmen continuously assess and refine the mold, making necessary adjustments to ensure its optimal condition for aluminum casting. Their keen observation and problem-solving skills play a pivotal role in mitigating any potential issues that may arise. As the mold nears completion, the craftsmen perform final checks, inspecting every aspect to guarantee its readiness for the casting phase. This thorough examination signifies the dedication and commitment to delivering a high-quality mold that meets stringent standards. Creating nail nippers is a meticulous craft that demands precision and dedication at every step. The journey begins with steel stocks, subjected to scorching temperatures exceeding 1,000 degrees Celsius. This extreme heat primes the metal for the shaping process ahead. Under staggering pressure, about 400 tons, the heated steel undergoes forging, where its structure is transformed and strengthened, yet only the most impeccable 30% of the forged steel advances, marking the uncompromising standards set for quality. Perfection demands sacrifice, and a considerable amount is discarded to maintain the standard of excellence. The next phase, grinding and polishing, unveils the distinctive Sawada quality. Here, an array of specialized sandpapers is employed, each contributing to the meticulous refining of the metal's surface. It's during the grinding and polishing that the true essence of Sawada craftsmanship emerges. A single pair of nail nippers journeys through over 30 meticulous steps in the polishing process alone. This phase relies on the expertise of numerous artisans, each contributing their skill to achieve the epitome of form and finish. The skilled craftsman, with a patient and methodical approach, breathes life into the nippers. Through minute, step-by-step trimming, the defining edge is carefully honed into existence. Each movement is deliberate, cautious, for there is no room for error. It must be perfected from the outset. the craftsmanship extends to the alignment of the facing blades. A craftsman's trained eye and steady hand ensure that once adjusted, the blades meet seamlessly when closed. The hallmark of true craftsmanship lies in this minute attention to detail, ensuring absolute precision. The handwork, methodical and cautious, demands unwavering dedication. There is no margin for error. It must be flawless from the very beginning. Such a relentless pursuit of perfection is the hallmark of Sawada's nail nipper manufacturing process, a testament to the fusion of skill, precision, and unwavering commitment to excellence. The production of pliers commences with metal blanks, the foundation of the tool's various parts. These blanks are subjected to intense heat in a potent electric furnace. The steel quickly reaches a malleable state, enabling metal workers to shape it on stamped forms. A colossal press then applies immense force, sometimes necessitating up to 4 strikes per blank, to mold and shape the handles, pivot, and jaws. The precision doesn't stop there. The jaws require fine teeth for their functionality. The plier halves are inserted into a machine equipped with multiple tiny blades. These blades cut through the steel like a flowing stream, cooled by a mist, resulting in each half boasting a row of finely crafted teeth upon exit. Strength and durability are vital attributes for pliers, demanding a rigorous heat treatment process known as tempering. The plier halves endure a 2-hour exposure to temperatures exceeding 800 degrees Celsius in a gas furnace. Post-furnace, they're rapidly cooled in salty water to fortify their structure. To further enhance their resilience, laser treatment toughens the teeth, ensuring they stand up to challenging tasks. Assembly marks the convergence of these meticulously crafted components. Inserting a pivot pin and joining both halves forms the pliers. High-speed machinery spins the pin with substantial force and friction to firmly unite the pieces. For slip-joint pliers, the process varies. A press secures the pivot bin using heat and pressure. The plier halves then undergo grinding between 2 stones with cooling emulsion to align the pin's surface, followed by another round of tempering in the gas furnace. However, instead of salt water, they're immersed in an oil solution for cooling. The refinement of steel demands precise thermal treatment to meet stringent quality standards. Subsequently, the pliers are submerged in a bath with an anti-corrosive compound, ensuring protection against rust while lubricating the pivot joint. Fine-tuning comes next. A robotic arm meticulously guides the pliers to a grinding belt, meticulously polishing every surface except the handles to achieve a smooth finish. Utilizing laser technology, the company's logo and product numbers are etched onto the tools, adding a touch of branding and identification. The final touch involves coating the handles. A liquid vinyl bath ensures a drip-free finish for hundreds of pliers. Slip-joint pliers are heated before dipping, allowing the coating to adhere securely to the steel. Once dipped and cured in an oven, the protective coating solidifies, creating a cushioned grip, improving the tool's ergonomics for ease of use.